And thank you very much for joining this event tonight. So I'm gonna share my screen now. So the topic for tonight is gonna be the sea breeze, and we are going to cover 6 different parts. So in part 1, we're gonna understand the sea breeze, and we're gonna build a model of the sea breeze. In part 2, we're gonna take this model into the reality, and we're gonna see real factors that influence the sea breeze. In part 3, we're gonna leave all the theory behind, and we're gonna get on the water, on the boats, and understand the signs so you can read the sea breeze signs. In part 4, we're gonna look at what are the best weather models that forecast the sea breeze. And then we're gonna finish by a quick part 5, with some caution and possible dangers with the sea breeze. And finally, we're gonna finish with the night breeze. All those parts are for day breeze, which is the most interesting for day sailing. And we'll just finish by talking briefly about the night breeze. So let's get started with part 1. What is the sea breeze? So this is a definition. So I'm gonna just read it with my French accent. A sea breeze is a cool onshore wind that develops during the day when land heats up faster than the sea, causing air over the land to rise and be replaced by cooler air from over the water. So this is all good, but for me, this kind of definition, I forget it. It enters from one ear and then I forget it. I am a visual person and I like to see an image, and together we're gonna build a diagram, a model of the sea breeze so it makes more sense and we can remember it. So let's start with this, a very simple image. So right here, we've got a coastline, a straight coastline with no topography, and next to it, the sea. Okay, and let's place ourselves in summer when the sun is rising. So by 10 a.m., sun is going to be up, and the temperature over land is going to increase a lot. It's going to be much warmer over land than over the water. And so the effect is going to be that the air over land is going to expand. The density is going to decrease, and it's going to make a thermal low over the land. Just have some technical issue with my webcam. I think it doesn't matter. You just look at the recording. So this creates what we call a thermal low on the ground. Because you've got lower pressure relative to over the water, what it creates a wind blowing from the sea to the land. This is a colder wind, and this is why we used a cold front symbol here. When this air reaches the land, it acts as a lever and is going to help the rise of the warmer air that has been warming up over land. This air rises, it cools down, it compresses, and the pressure, and you get a higher pressure over here. It's quite important to understand that this is higher pressure, but at this level, okay, around this vertical level. Of course, the pressure is higher on the ground, so don't be confused by this. Anyway, because we have a higher pressure in altitude than the surrounding, it's the same way. It's going to create a wind in altitude flowing from the high pressure to the lower pressure back to the water. This wind is going to cool down over the water and it's going to sink. And by sinking, it's creating the high pressure over the water that we mentioned earlier. So this is the end of the loop, and the sea breeze has been created and is going to keep rotating, okay? So the topic of today is the sea breeze. So this is this onshore flow blowing from the sea to the land. And this diagram, the source is from NOAA. And we're actually going to refer to this diagram quite a lot during this presentation. So I hope it makes sense for everyone. But as a quick way to remember, the big takeaway is the sea breeze is like a big giant wheel with at the surface an onshore flow and in altitude an offshore flow back to the water. So now the model has been built, and we're just going to look at, okay, the sea breeze for a sailor in numbers, what it is. So roughly the sea breeze is an onshore wind blowing 10 to 20 knots. Of course, there are some light sea breeze. It's more a 5 to 10. Moderate is 10 to 15. And a strong sea breeze is 15 to 20 plus. Something important to notice is the vertical extension of the sea breeze. So it's about 1 kilometer or 3,000 feet, and it's equivalent to the level corresponding to 900 millibars. And the sea breeze also extend. So it extends at sea around 10 to 100 kilometers, which is 5 to 50 nautical miles. So for example, if you are sailing the Atlantic Ocean and you are approaching Europe, you will not feel any sea breeze if you are more than 100 kilometers at sea. And this is like a typical sea breeze day. Of course, those timing are just indicative, but roughly from 8 to 10 a.m., you've got no wind or maybe calm offshore wind. 10 to 11 a.m., the sea breeze starts to fill in slowly. It's onshore and it's quite patchy. From noon to 2 p.m., the wind builds from the shore and extends offshore. From 2 to 4 p.m., the wind reaches its maximum speed in the early afternoon. This is usually when the land is the warmest and the sea breeze holds. And after this, around 4 or 5 p.m., the wind is going to decrease and it's gonna die out. Still trying to fix my webcam if I can. Maybe I can try like this. Okay, no problem. Let's go into the part 2, which are the factors influencing the sea breeze. So what I call the reality factors. So this part is quite exhaustive. We're going to look into 7 factors. We're going to start with coastline, topography, cloud cover. And I really hope that some of those factors apply to your local spots where you sail, and it makes sense. And what we're going to look at is how those factors, influence some part of the sea breeze, some part of the wheel. And the way it works is if one factor helps the sea breeze, it's like a booster. It's going to help the wheel spin faster, making a stronger sea breeze. Some other factors may do the opposite and may prohibit and kill the sea breeze. So let's start with this. So the first factor is the coastline. So the coastline can influence greatly the strength and also the direction of the sea breeze. So here I have listed like 3 basic coastline shapes. The first one is a straight coastline. So in this case, you're going to have an even linear sea breeze. It's going to be quite predictable, and the strength is going to be roughly medium. You have another type of sea breeze, which is concave, this kind of shape here. And the coastline here is going to focus the sea breeze toward the center. And usually it's a stronger sea breeze. And finally, we have the convex shape. In this case, the sea breeze tends to be dispersed or it's split. You have very different type of sea breeze on one side or the other. And usually it's a weaker breeze. And this is typically what you have around some cape for example, Cape Cod in the US. So here I've just represented the straight coastline of Miami right here. And the wind I'm putting here, this is the PredictWind PWG 1 kilometer very high resolution model, okay? And this one is for Naples in Italy, where you can see a lot of details, a lot of granularity of the wind forecast in the bay. So now let's move into the second factor that influence the sea breeze, the topography. So mountains or hills near the coast can enhance or disrupt the sea breeze by channeling or blocking the wind. So it happens a lot around lakes, near mountains. In this case, we talk about lake breeze. In this talk, I'm only going to talk about the sea breeze, but everything applies to a lake, okay? So we can take the example of the Garda Lake in Italy. So this lake is surrounded at the north by mountains, and during the afternoon, those mountains heats up a lot. The air warms up because the slope of the mountains are facing the sun. And the air remains cooler over the lake or even over the valley. The consequence is to create the sea breeze, blowing from the colder to the higher. So this is a sea breeze, but you can also imagine the breeze going up, the return flow in altitude, and then going down. So it's exactly like at the sea. And on top of this, the wind is channeled by those mountains, making the wind strong and very reliable. This is why there is plenty of sailing happening in the Garda Lake. So now let's move into the third factor, which is the cloud cover. Okay, so let's say in the morning you have a cloud cover over land. It's going to actually block the sunshine and limit how much the land can warm up, which is not good for the sea breeze. So if you have a thick cloud cover, it may prohibit the sea breeze from developing at all. Inversely, if you have a little of cloud cover over the water, okay, then in this case, it's going to actually help the differential heating between land and water. And it may result in quite a good sea breeze day. So as you can see, the cloud cover, it's quite fine factor. It really depends where it is. If you want even more complexity, I had it here a notes, is because the sea breeze has this rising air, it means that there's going to be some cloud formation over land because of the rising air. So there are some cases where the sea breeze actually develop early, and very early, too early, they create those clouds over land, and it will not help the temperature to keep going up. So in this case, the sea breeze will almost like self-destruct. So I'm giving those examples just to show you that clouds are very complex, and maybe it explained why sometimes you are at the beach and everything look good by 10 a.m. and you think, oh, it's going to be a good sea breeze day. And then there are those clouds, and actually the sea breeze may not happen. Clouds are very complex. Another factor are if you are in a region where there is very large air temperature difference between the land and the water. So there are some parts of the world where the coastline gets extremely hot during the day and the ocean remains cold. And those make perfect places for strong and consistent sea breeze. So let's get an example. So in the south of Morocco, the Sahara Desert get extremely hot during the day, talking 50 degrees Celsius, and it's next to a cold Atlantic Ocean, and it creates a sea breeze every day. It is the same on the other side of the world. In Australia, for example, Perth, the outback gets very warm, and it's next to a colder Indian Ocean. So those places actually are famous among windsurfers, kite surfers, And usually they go to those places because they know the sea breeze is going to be reliable. You go there for 1 week, you're going to have 6 days of sea breeze, and it's going to be strong. Myself, when I was younger, I went to the south of Morocco for windsurfing, and it was 20 plus knots every afternoon. The only downside is the ocean was cold, so I had to wear a full wetsuit. So now let's move into another factor that can influence the sea breeze. This is the vertical stability. And the vertical stability plays a role in how the air is going to rise over land. So let's start here. What is a stable system? So if I push a little this orange ball and let it go, the ball is just going to go back to where it was. On the contrary, an unstable system, if I push this orange ball just a little, it will keep going and fall all the way down. This concept of stability can be applied to the atmosphere. So when we talk about an unstable atmosphere, we are talking about the vertical motion. So it means that if an air parcel rises a little, it's unstable, so it will keep going up even faster. So the instability boosts the rise of the air and therefore helping the sea breeze. A way to remember it is instability is like vitamin C or like steroid, and it just helps the rise of the air. A visual clue of the instability, for example, is formation of cumulus clouds by midday over land. So those are the cumulus clouds. So if you see them, popping up over land around 10, 11 a.m., it's a good sign that there is instability and the sea breeze is likely to happen. On the contrary, a stable atmosphere is the stability prohibits the rise of the air, which is not good for the sea breeze, okay? And it's almost like a tranquilizer pushing the sea breeze down. An example, typically, when there is a temperature inversion in the atmosphere, this is very stable. So here is a picture. So somebody is doing a fire. The fire helps the air to rise, but it hits a stable atmosphere and the air cannot go further up. It's just a ceiling because of this very stable air. Okay, so maybe some reasons why you may have instability. If the air is very warm, if there is humidity in the air, the humidity is potential energy and it may be released and create instability. If you have also colder air in altitude, the contrast will create instability. And another one is gradient wind. And I mentioned this one because we're going to study it just after. But there are other reasons when there is instability in the atmosphere. And the instability, please remember that it is good for the sea breeze. So let's go back to another factor that influence the sea breeze. This is the gradient wind. So in part one, when I showed this diagram from NOAA, I said that, in the model, in the morning, there is no wind, no gradient wind. But the reality is often in the morning, there is a background wind due to a large scale weather pattern. So this wind is referred as a gradient wind. The full name is pressure gradient wind, or some people call it synoptic wind. So here I'm showing a map from PredictWind. This is an isobar map with those pressure contour lines. We've got a big low pressure approaching island. And the pressure gradient wind is the wind that blows along those isobars. And as you can see it here, when those strong winds will hit, for example, the west coast of France, the sea breeze is not going to develop because the gradient wind will take over. So the gradient wind can impact the sea breeze in two ways. The first one, it may impact the return flow in altitude. This is criteria number one, but it also impacts the instability, and therefore the rising in 3. So what we're going to do now is just study those two criteria one by one, so it makes a lot of sense for everyone. So if you have some offshore wind in the morning, it can help the sea breeze. So by saying some, it's almost like salt. You want a little, but not too much. If it's too much, as I said before in this isobar map, it will take over. But if you've got a little bit, the right amount of gradient wind, it may help the sea breeze. And why is that? Is because this gradient wind in altitude will kickstart the sea breeze, okay? The return flow is already present, and so it will help spin the wheel. As soon as the air rises, it will be pushed over the water, therefore creating the rotation in the sea breeze. So the negative criteria for the sea breeze is having a strong gradient offshore wind. Okay, if it is too strong, it will not work. And especially, you know, at the surface. At the surface, if the sea breeze is too strong, the onshore flow will fight against it and it will not wind. So you will have no sea breeze. But if you've got the good amount, I will say weak or moderate offshore wind in the morning, less than 10 knots, it's usually a good criteria for the sea breeze. It's better than having absolutely no wind. And here on the screen, I'm putting a question that a professional sailor asked during a weather briefing before race. Is the question they ask is today, is it going to be a gradient day or a sea breeze day? So by gradient day, it means a strong gradient taking over or a sea breeze day. So you need to answer one or the other. But as I explained today, sometimes it's a little bit finer in details, meaning if you have a bit of a gradient in the morning, it will help make a good sea breeze in the afternoon. So now let's move into the second criteria, how the gradient wind impacts the instability and the rising of the air along the coastline. Okay, so here the angle between the coastline and the wind direction impacts vertical stability at the coastline and therefore the capacity to rise. So there is some physics for this. So I'm just going to explain as simply as I can. Okay. So the physical things we're going to see is the friction. Friction is greater over land than water. This has an impact on the horizontal wind shear. It will impact what we call the positive vorticity. And all those things combined are going to create the rising of the air. So this is a lot of technical words. I'm going to try to explain it simply by providing some pictures. Okay, so let's talk about the friction. So here is a straight coastline, and I put here an altitude scale, okay, at the surface and at the top of the sea breeze, okay. And let's assume, okay, we have in the morning a gradient offshore wind of 50 knots at 1 kilometer high. Then, of course, it's going to be a bit slower, 13 knots. But at the surface, it's going to be offshore, 10 knots. What's interesting is over the water, it will be a bit faster. I'm putting here 11 knots. Okay, those numbers are not written in stone. It's just an indication. But the reality is just that the wind is slowed down over the land because of the friction over the mountain, over the trees, and over the water, it's smooth, so it goes faster. So this is the friction part. But this, you may say, oh no, this does not create any lift, any vertical instability. But if the wind is not perpendicular to the coastline, but has an angle, then things change. So this, on the left, I still have the land. On the right, I still have the water. And this is my main wind, okay? It's not blowing perpendicular, but it comes with an angle. So this red square is an air particle right at the coastline. And as you can see, on the left side, it's 10 knots, and on the right side, it's 11 knots. And the consequence is going to make this particle turn, spin. And by spinning clockwise, it creates what we call positive vorticity. Then there is some physics behind it, but the particle is going to stretch vertically, is going to spin faster, and is going to create a vertical motion of the wind if it turns in this sense, counterclockwise, in the North Hemisphere. If you want more information, you can go to the help article. As a takeaway, what I really want you is to remember this. They are strong quadrants. So if you are in the North Hemisphere and the offshore wind in the morning is 5 or 10 knots from this quadrant, it will help the sea breeze because of the instability. A way to remember this is a low pressure system in the North Hemisphere. As you can see, it turns counterclockwise, and this is the same reason this particle has to spin counterclockwise to rise. The same way air rises at the center of a low pressure. And of course, if you are in the South Hemisphere, this is the opposite. It turns the other way around. So now let's look at the last factor, which is the Coriolis force. We have a great article called Wind in our help center that explain everything about the Coriolis force. As a quick summary, the Coriolis force push objects to the right in the North Hemisphere. And this is a question that sometimes people ask, sailors ask, is does the Coriolis affect the sea breeze? And the answer is it depends. It depends on what? If you've got a strong sea breeze, I will say 15, 20 plus, there is a good chance the Coriolis force will have an impact. If you are dealing with a widespread sea breeze, that extend over 100 kilometers, then the Coriolis force will have more time to actually push the wind direction to the right. And of course, you need to be away from the equator. I would say if you are in the mid-latitude, there is a good chance the Coriolis force may be felt, okay? And as I was saying, if those conditions are met, you can expect a right direction trend in the North Hemisphere. And now what I want to do together is to focus on this and take a real example of a real sea breeze. And we are going to talk about Valencia in Spain in the North Hemisphere, a place that I know quite well. So Valencia hosted the America's Cup in 2007. I was part of the weather team for Team Alinghi. Valencia is a very large concave bay that favors a sea breeze. It extends all the way to the south by 80 kilometers, so it's widespread. And it's also very warm, sunny, and dry during the summer, perfect for sea breeze. On top of this, you have also some topography inland. So here I'm showing the PredictWind PWG 1 kilometer for actually today. And you can really see on this map the sea breeze developing. So there is no more sea breeze 100 kilometers outside, and it goes also inside. And you see the westerly here. So the PredictWind model really captures well the sea breeze in Valencia. And here it's for today, the graph for the wind direction at Valencia, at the center of the bay. And you may be able to see the direction having numbers increasing, meaning the breeze going right. So I've just zoomed around here, and around 2 to 5 p.m., we have this right trend, and the wind went from east to east-southeast, which is very typical, and the breeze was strong today. So this is when I was in Valencia, we often notice it, strong breeze, turn right. So I cannot tell you it's because of Coriolis force, but this is the physics, and it has to play a role. There are other reasons, topography, cloud cover, but this is always a possibility in the North Hemisphere. So here are some pictures of Team Alinghi. Back in 2007, we were dealing with non-falling boats with keel. And here is the weather boats that we were using during the America's Cup to measure the wind. And this is the weather team. And luckily, we won the America's Cup. And at the center of this picture, this is John Bilker, which is owner of PredictWind. After Alinghi, he created PredictWind. So PredictWind DNA is really the America's Cup, and a lot of the technology that we developed during the Cup was used after to build our models. So now we have finished with all this technical meteorology stuff. I hope people are still with me. And we're going to move in something more practical. We're going to get on the boat and look at the signs so we can read the sea breeze. So what are the positive signs? And those positive signs, you know, they will make sense for you because in fact, they are based on all the theory we've seen before, okay? So if in the morning you have clear sky and strong sunshine, especially on land, it will help create the temperature contrast between land and sea, which is good for the sea breeze. And usually you have this type of clear sky if you are in a high pressure system and if the weather is stable. If you have calm or even better light offshore wind in the early morning, it will help the sea breeze. By 11 a.m. also, if the wind drops completely, this is also a good sign. It means the wind is going to reverse and is going to turn from offshore to onshore. If you see some cumulus clouds developing over land, another good sign. And finally, on some days, you may be able to see the sea breeze front visible. So it's usually a thin line of cloud, of haze. You can sometimes see a darker line on the water. This is the wind coming. And this marks the advancing of the sea breeze. Of course, there have also some negative signs, which is overcast sky, if you have no temperature contrasts, if you have a strong gradient, as we mentioned before, if you are in a low pressure system with unstable weather and rain, this will not help the sea breeze to happen at all. Now, to finish this part, I want to talk about something kind of a sign of the sea breeze. I'm talking the signs when the breeze is shifty. Shift means that the direction of the sea breeze will change, or maybe the wind speed will change. And this is very typical. In Valencia, for example, we experience shifty sea breeze all the time. So this is, you know, the models that we built before, which makes very steady winds. But the reality is, as I was saying, Valencia is shifty. A lot of sea breeze are shifty. And the reason it's shifty is because a more realistic model is something like this. You have turning sails within the big sails, and this creates shift. So for example, if you have the main sea breeze blowing at 10 knots, and let's say you are here under this little sail, as you can see, the breeze will be a bit faster because it's being helped by this loop. And so it will blow 11 knots. If you are over this one, it's going to be the opposite, and it's going to blow a little bit slower. So if you are a sailing boat sailing upwind, you will experience change, you will experience these shifts, both in knots, but also in direction. And typically direction shifts are around maybe 10 or 15 degrees. And this is, you know, some of the strategies that we use during the America's Cup. So if we were early, when the sea breeze was developing, so the sailors, usually they play the pressure and they sail towards darker patches on the water. But if the breeze is well established, and usually the umpires wait for established sea breeze to start the race. In this case, the sailors will tend to play the direction shift to find the quickest way to the mark. To explain this further, I have taken this image from MPI.com, and it's a good way to visualize a sea breeze. And you will be surprised that actually some sailors from the America's Cup, they actually refer to this. They refer to sailing through the breeze, sailing through tubes, okay? They refer to like right shift tube. And this is what they are experiencing when you are sailing upwind. So if you are a boat here and you want to go to the mark, and let's say this tube here is creating a left shift, and the one after is a right shift, sailors will go on port tack to this one, and then they will tack and go another one, going all the way through those tubes because of the shifts. So this, you cannot see it on the water. I've never seen it, but there are some special circumstances where maybe there is some humidity in the air, and sometimes you may be able, to see the top of those cylinders, those tubes, just with some clouds. And this is just an indication that there are those tubes of shift within the sea breeze. So this can help you maybe win a race. So now we're going to move into something different, is what are the best weather models that PredictWind can give you to forecast the sea breeze. So in order to forecast a sea breeze, you need a high resolution model capable of displaying land and thermal effects. For example, a global model like GFS, 25 kilometer resolution, will not be able to capture well the sea breeze. So PredictWind, we offer all those regional model. Regional model means it's the opposite of a global model, okay? So we have two in-house model. We call it PWG 1 kilometer and PWE 1 kilometer. They cover the entire world, only on the coastline. So those are the popular coastlines in the world, like USA, Europe, Australia, New Zealand, etc. Then we also offer HRR, which is just for North America, NAM also, and for Europe, we have ARON and UKMO. So if you want to know where those high resolution models are available, you can go to predictwind.com/world coverage, and you will see all of this. So for example, this is a NAM model available over the US. This is UKMO and ARON, and all those little square. This is a PredictWind high resolution model available on the coastline. So if you are sailing in the Caribbean, we have it. Western Australia, we have it. So now we're going to move into the caution and potential dangers of the sea breeze. Okay, so sea breeze is only 10 days, it's only 10 knots. Not always, not every day. So I'm sure you are good sailors, but those are some good things to keep in mind. So what is a danger? So because the conditions are usually very calm in the morning, they can turn windy in the afternoon, okay? And the wind direction will change completely. So I've put the picture of this rental boat here because quite often people, renting some boats, they go in the morning, looks completely calm, and it might be 20 knots in the afternoon. Another danger with the sea breeze is related, to the coastline, as we discussed before, the convex shape. The sea breeze can be very different when you go from one bay to another. And so you need to be careful when you change a bay. You may need to reef and conditions may be very different. And one of the last danger that we can list for the sea breeze is because we have rising air and cloud formation, even if they start in the morning as small cumulus, sometimes, especially if you have high instability, they will develop as big, powerful cumulonimbus. Okay, in the late afternoon, it's common, especially over land, to have those big cumulonimbus form. They are associated with strong gust, heavy rain, lightning. So they might impact, the coastline when you go back to the port at the end of the sail, or sometimes because of the return flow in altitude, they may, at the end of the afternoon, move on to the water. So this happens. So the bottom line is you always need to check the weather forecast before going out, even on a sea breeze day. And now we're going to finish with the night breeze. So the night breeze, this is almost the opposite. You know, at night on land, the temperature decreases rapidly, but they will tend to stay warmer over the water because the ocean acts as a regulator, as a temperature buffer. And so it's going to create a wheel, a spinning wheel, exactly the opposite. And it creates an offshore sea breeze at night. So similarly, we've got this picture by Noah, and as you can see, is exactly the opposite. And to finish, the night sea breeze for sailors. So usually, you know, the sea breeze starts in the middle of the night or until early morning. The night sea breeze is weaker than the day sea breeze. It tends to be less gusty. It's smoother, and usually water is more calm, especially because it's offshore. I believe that it can be useful, you know, for cruisers, for example, who wanted to cover miles at night with moderate breeze. But of course, you need to be careful about potential hazards of sailing at night along the coastline. And finally, you know, the sea breeze can be felt if you spend the night at anchor. So you need to be careful for this wind rotation. You know, when you arrive in the afternoon, you anchor with a certain direction, but the night sea breeze will be 180 degrees. So the boat may swing. And finally, I tell you, yes, the breeze is calmer, smoother at night, but still you have some topography effect in an anchorage, and some anchorage, they can actually have a strong sea breeze, and you may have a strong offshore wind waking you up because the anchor is dragging. So this is it, and we are now at the end of this presentation.